So we've learned the rules for naming ionic compounds. Now we're ready to learn the rules for naming molecular compounds. We have to write the formulas if we're given the names, and write the names if we're given the formulas. Go in both directions. Okay? The good news. The good news is these rules are very simple to use. You don't have charges. There are no charges in molecular compounds. They're not made up of ions. They are not ionic compounds. There are no charges. Okay, so what's the rules? Well, forget the rules. Let's remind ourselves. If it's a molecular compound, they have discrete molecular units, and it's going to be typically a nonmetal connected to a nonmetal. Okay? Might be multiple nonmetals, but in there, if they're nonmetals and there's none of these polyatomic ions present, we're dealing ourselves with a molecular compound. Okay, so what's the rules? You name the first element first, you name the second element second, you give the second element an IDE ending, similar to our ionic compounds where the second element that was an anion got an IDE ending. So we see a similarity there. That's the first rule. Okay, so silicon carbide. This is really not a good example of a molecular compound, but it follows the rules. So if you look at the periodic table and find silicon, it's actually it's a metalloid, and metalloids follow these rules as well. A metalloid to a nonmetal would be like naming molecular compounds. So silicon was first, we name it silicon. Carbon is second, give it an IDE ending, and this is silicon carbide. Okay, second one. If there's no charges, we can't figure out how many there is of the elements by using the charges, so we have to be told specifically how many of each element we have. Okay, so we're going to use prefixes before these names. So I've got silicon, I've got carbide. There was just one of each, so we don't need these prefixes. But if there's more than one, we will use prefixes to tell the person how many of each element is present there. All right, so what prefixes do we use? Sometimes we'll use mono for one, and we'll see why and when. But the other ones, di 2, tri 3, so far so good. Tetra might be one that you're not very familiar with. Tetra means 4. Penta, pentagon, for example, has 5, okay? Then hexa. Hepta is another one that we don't see very often in the world of shapes, and heptagon, but it is used here in chemistry quite often. So if there's 7 of it, it's hepta. Octa, think of an octave in the piano, or an octopus, 8, okay? Nona is another one that's not real familiar to people. And deca, I think most people are thinking about decades. You've got 10 years in a decade. So those are the prefixes that you need to know. And now let's use them. PCl5. Now, first thing I have to do is realize that this is not an ionic compound, and I'm using the rules for molecular compounds. Now, how do I know it's not ionic? I look at the periodic table, I find P, I find Cl. I see both of those are nonmetals. So I'm going to say, I'm not going to use an ionic rule, I'm going to use these molecular rules. I told you the good news was the rules are a lot easier. The bad news is people want to use the ionic rules all the time because they learn them first, regardless of what they are. So you have to stop and think, which rules do I use? Okay, so how would we name this? Well, the first element is called phosphorus. The second element is called chlorine, but we give it an IDE ending. But how many of them are there? There are 5 of them. So here would be the name, phosphorus pentachloride. Now, something to look at. We don't use mono with the first element if there's only one of it, okay? So we would not call this monophosphorus pentachloride. We call it just phosphorus pentachloride. So make sure you keep that aware. Be aware of that. Okay, the next one, N2O4. Okay, so we don't have only one of the first element. We have 2 of the first element. The first element's name is nitrogen, so there's 2 of them. And then there's 4 of the oxygens. I'm going to use the molecular rules because when I look at the periodic table, I see that nitrogen and oxygen are both in the top right-hand corner of that periodic table. So I know that this is going to follow the rules of being a molecular naming system. Using prefixes, we tell how many there are. So dinitrogen tetroxide. Tetra for 4. Now, this is very subtle, but it's the way it is. something to note here, when you have oxygen and you have a prefix telling you how many oxygens you've got, you're going to drop the ending, that A. We don't call it tetraoxide, okay? That's very subtle. We're not going to call it tetraoxide. We're going to drop that A and we're going to call it tetroxide. If there was a prefix like di, you don't drop the I. It's dioxide, okay? Trioxide. But penta, drop the A, pentoxide. Octa, drop the A, gosh, I don't even know how I can say that. Octoxide. Whew, I don't think I've ever said that word. There must not be too many compounds out there that have 8 oxygens. Okay, there are some common exceptions. I want you to be aware of the fact. I want you to know that, yeah, not everything out there gets named by this nice systematic system that we're learning. Why are there exceptions? Because the name of the compound got really ingrained in our language before this system was developed. And so we couldn't let go of the name. I'm going to give you an example right off the bat before we write anything up there. Water. Nobody calls water dihydrogen oxide. Dihydrogen monoxide, hydrogen oxide. I mean, they just don't do that. They call it water every time because we had water ingrained in our world way before we came up with the system. So there are a few. It looks like most of these are the smaller, more, what should I say, the smaller hydride, hydrogen-containing compound of some of these nonmetals, okay? So diborane instead of diboron, hexahydride, and so forth. So you don't need to memorize those. You do definitely need to know that one, okay? We will use this one fairly frequently, and you might run across this one. We've already this semester talked about methane a little bit. So those would probably be the ones that you would see more frequently, but you just be aware that there are some simple compounds where we stick with their common name and don't use their systematic name. All right. That's just a schematic of what we just walked through there. And so we'll practice a few more. Okay, OF2, I'd like for you to stop and see if you can use the system. Well, I'll help you with the answer. You've resumed. Did you call it oxygen? Not oxide, because this is the first element. Oxygen difluoride. Okay? When you do your homework system, you have to spell it correctly. You can't come to me and say, I got it right, I just spelled it wrong. Make sure you, and I'm telling you, I'm the worst speller in the world. I still have to write it correctly. And a real common mistake for students is to call or spell flour. You know, the flour that you cook with? There is no flour in fluorine. We're just so used to writing F-L-O-U-R that when we type it, we write F-L-O-U-R-I-D-E, and it's U-O, fluoride, F-L-U-O, okay? All right, try this one, P4O10. Stop, give it a name, and let's see if you got it right. Did you write tetra, because there's 4, phosphorus, okay? Tetra, phosphorus, because there's 4 of those, and we keep the ending the same as the element. And then 10 is dec, and we drop the A because it's oxide, okay? Phosphorus is another one that students very often misspell. Make sure you're careful, O-R-U-S, not O-U-S at the end, okay? Tetraphosphorus decoxide. All right, now we're going to give the formula if we're given the name. It's super easy to do this. Carbon, they're not giving me a prefix, so I know it's 1. And tetrachloride, I have 4 chlorines. Easy enough. Now you try the next one. Sulfur hexafluoride. Pause, come up with a name, resume. 1 sulfur, 6 fluorines. That's how you do that. So, good news, Simple system. Can you see how simple this is? Did we have to go and figure out charges? There are no charges. So we do not have to worry about we don't have to come up with charges in order to come up with a good formula. They're going to spell it out for us. They're going to tell you how many of everything you have in order to do that. But don't say, well, I love this system, so I'm going to apply it to the ionic world. We can't do that. We have to use this system and only this system for our molecular compounds. So when we're doing our work, we always have to, we're asked to name something. When we write a test, for example, or you're doing your homework, we're not going to say, name this molecular compound. We'll say name, and we'll give you a formula. So you have to figure out which system you have to use. And that's the biggest challenge for students. It's not how to use the systems, they're easy. It's using the right system for the right one. So let's practice that. Here we have BCl3, okay? Before you ever try to give a name for this, you have to stop and think, which is this? Is this an ionic compound or a molecular compound? Look at a periodic table, pause, look at a periodic table and choose your answer. Did you say it's a molecular compound? Then you are correct. Now it's not a non-metal. It is a metalloid, non-metal, but those will fit into the world of molecular compounds. You will use the molecular rules for that. Okay, so once you've decided it's a molecular compound, then you can name it, okay? Pick the right name, pause, think, choose. Okay, did you choose C? If so, you can pat yourself on the back, patting yourself right now. Why did we have to use the try? We had to use the try because there are 3 of those chlorines and we have to tell the person because they can't go to the periodic table and figure out charges. Molecular compounds don't have charges, so we have to tell them that there are 3 of the chlorines. Okay, next one for you to try. We're going to do iron 3 sulfate, and we're going to come up with a good formula for it here in just a minute, but we have to know the system that we're using here. So which do we have? Do we have an ionic compound or molecular compound? Look at the periodic table before you try to choose. Well, if you said it was an ionic compound, you are correct. Iron's a metal. Well, sulfate's not a nonmetal, but it's a polyatomic anion. And we are going to now come up with a good formula for it. If the name is iron 3 sulfate, stop and look at your choices, look back at the rules of ionic compounds, and come up with the right answer. Okay, if you chose E, you'd be correct. If you chose anything else, listen to the explanation. You've got to start by knowing it's ionic, so we're dealing with ions. Ions have charges. How do I know it's got a 3+ charge? It's got a 3+ charge because that Roman numeral 3 tells you the charge. All right? Now sulfate. Sulfate. Can I get this from the periodic table? No. How do I know that? It's only known by memorizing those polyatomic ions. So now I know its formula and its charge. Now I need to come up with a good formula that has as many cations as it has anions. And so let's think about that. Least common multiple between 3 and 2 is 6. So get 6 positives and 6 negatives. A way to do this might be the crisscross down method. So we have 2 irons and we have 3 sulfates. And if we have 3 sulfates, we put parentheses around the sulfate and put the 3 outside of that. So that's how I know that E is the correct answer. Last thing I want to leave you with here today, oh no, it's not the last thing, it's almost the last thing. We've got a little bit of nomenclature for acids. We need to define acids and look at the system for that. Now the system for acids is somewhat complex. Bad news. Good news is we're not going to make you use it for the more complex ones. We're going to learn the simpler acids and leave the other ones for later. Okay, so compounds that produce H+ ions when they're dissolved in water is one of the definitions of an acid. If you put it in water and H+ ions pop of that acid and float around in that water, then you're dealing with an acid. So, some of the things that we know about acids property-wise, they taste sour. Whenever you taste something that tastes sour, it's an acid. So lemon juice has an acid in it, okay? A vinegar has an acid in it, these sour things. I don't want you to go into the lab and tasting acids and seeing which ones taste sour. Take my word for it. Okay? Another property of acids is they will dissolve many of your metals. Not all of them, but many of your metals will dissolve easily in an acid. They can be divided into two main categories, okay? There's binary acids and there's oxyacids. What is an oxyacid? Well, it would be one that contains oxygen, okay? So H2SO4 is an oxyacid. Binary acids only contain two elements. Now, that doesn't mean it only has, well, let's write it one, HCl. That contains a hydrogen and a chlorine. But it could also be something like H2S. Okay, that would be considered a binary acid. If you dissolve it in water, it would produce H+ ions. That's a binary acid. It has two different elements, one of which is going to be hydrogen. So it's going to have hydrogen plus one other thing, and that's going to be a binary acid. Now, for your binary acids, to name them, oh, and there's the examples. For the binary acids, to name them, you use this form, okay? You use hydro at the beginning. You name the metal, then you give it the -ic suffix, and then the word acid. Okay? So let's see how HCl fits that model. Hydro, okay? This combines with the name of the nonmetal, which is chlorine, and we give it an -ic ending. Hydrochloric, okay? And then acid. That would be the name of HCl. If it was instead HF, how would it be different? Well, hydro hasn't changed. Instead of chloric, it would be fluoric, hydrofluoric acid. That's how you name binary acids. Oxyacids. Oxyacids are the one that's more complex. But here's some examples: H2SO4, HClO3. These are oxyacids. Like, they contain an oxyanion, which we talked about before, and those are your polyatomic ions. So that's chlorite is the name of that guy. And then they have H's, as many H's as it needs to make it neutral. Sulfuric acid is based upon the sulfate ion that had 2- charge, and then we have 2 positives added to it, so it's H2SO4. Now, we are not going to test you on oxyacid nomenclature. It may be that when you're doing your homework that you need to know the names of some of these polyatomic some of these oxyacids. Be aware that you might have to look them up. Open your book and look at the names that are there, or do a quick web search and see the names there. But so you might have to know them to do your homework. I can't remember. I don't know for sure, but that has happened in the past. But you will not be tested over it. So I won't give you H2SO4 and you tell me it's sulfuric acid. I won't give you that kind of oxyacid, but I will give you the binary acids, and you should be able to name those as acids. Now, this last thing I want to mention is in section 3.7. It's just one page. It's a flow chart. It's on page 104. A flow chart of the naming system that might be, for those of you who are real visual people, helpful to see it as a flow chart system of how we name these differently than it's the molecular compound different than the ionic compound. So it kind of lays it out as a little flow chart. It might be useful for you to look at. And that ends our systems of how to name compounds, whether they're ionic or molecular.